All right, hi everyone. Welcome back to section 7.1. In this video, we're going to take a look at our second example of the Laplace transform, and this time we're going to apply it to a basic polynomial. So use the Laplace transform definition to transform the polynomial t. Okay, so t is, our f of t in this situation. Okay, so we want to use a definition of Laplace transform. Let's write it down just to keep it handy uh, when we start this problem. So, excuse me, oops. Laplace of f of t equals the integral 0 to infinity e to the negative st times f of t dt. Okay, so that's our Laplace transform definition. So let's go ahead and try this problem out. So what we will have is the Laplace of the polynomial t. It's going to be the integral of 0 to infinity e to the negative st times t dt. And remember that t is like our f of t that we're transforming. Okay, so let's check this problem out. So we have an exponential times a polynomial. What type of method do we need to use? We need integration by parts. So need integration by parts. Okay, so here u would be t and dv would be e to the negative st dt. Okay, and I'm following, Lipid if you follow that as well. T is polynomial, e to the negative st is an exponential, falling in this category right here, polynomials first. But let's go ahead and keep moving. Hopefully you're very familiar with this by now. So du would be dt, and v would be, like that mental u sub situation, negative e to the negative st all over s. All right, and so integration by parts, it's uv minus the integral of v du. So, we're just going to go cross some cross action. And so our integral becomes t, let me rewrite that, t times negative e to the negative st all over s minus the integral of 0 to infinity, forgot my balance here, sorry, minus the integral of 0 to infinity, and it's v du. So it's just negative e to the negative st all over s dt. All right, so let's clean up a couple things. Just drop the parentheses, move the double negatives. So what we end up with is, let's say negative t e to the negative st all over s, going from 0 to infinity, plus 1 over s. I'm taking out the constant s. We could do that because our variable of integration here, excuse me, is t. So that's what I'm left with uh, after simplifying. So then if I want to integrate, what I would end up with is, excuse me, let me forget my bounds again, 0 to infinity. What I would end up with, another mental u sub, right? We're going to be seeing this type of mental use of a lot with these Laplace transforms. What do we get is 1 over s, excuse me, plus 1 over s times, negative 1 over s, e to the negative st, going from 0 to infinity. All right, so simplifying, you could have did this in the previous step, but I just want to make sure we knew where 1 over s squared was coming from. Okay, but now we just want to solve these evaluations. So let's go ahead and start plugging in our bounds. So, what we get is, negative infinity e to the negative s times infinity all over infinity minus negative 0 e to negative s times 0 all over 0. Okay, so excuse me. So let me back up a little bit before we keep going. What I want to do is actually bring down the e to the negative st so that we're able to determine correctly where this term is going as it goes to infinity or 0. So I want to bring those terms down and get rid of the negative exponents. Okay, so let's do that. So this is going to be, negative t over s e to the positive st going from 0 to infinity minus 1 over s squared e to the st. Let me move this 1 over, and we're going from 0 to infinity. Okay, so now I feel more comfortable evaluating these bounds. So if we plug in these bounds, all right, this time this would be like infinity over s e to the s times infinity, mine brackets minus 0 over s e to the s times 0, okay, minus brackets, uh, 1 over s squared e to the s times infinity minus 1 over s squared e to the s times 0. Okay, so let's take a look at a couple things. Um, this is just 0 divided by s e to the 0, which is just 1. So this whole term just goes to 0 anyways. Okay, and this whole term, 1 over s squared e to the s times infinity, that's just 1 over infinity, and that goes to 0 only if stays positive. Okay, as long as s stays positive, this turns into 1 over infinity and goes to 0. Okay, and then this term all the way to the right, e to the s times 0, well, this just goes to 1. So this ends up just being like 1 over s squared if s is greater than 0. Okay, but there's one thing we need to observe right here, this negative infinity over s e to the s times infinity. Well, that is infinity over infinity. Okay, so this is kind of a limit we need to solve. So, we could say like note, set up the limit as t goes to infinity. If it's negative t over s e to the st, I'm kind of pulling this and coming down here. So I need to solve this limit, but we know we get infinity times infinity, excuse me, over infinity. So what's that rule we could use to solve a limit like that? That's going to be L'Hopital's. And that's where we take a derivative of the top and bottom if we have infinity over infinity. So this would be derivative of t is just negative 1. Um, the derivative of se to the st be careful here. S is just a constant. It's not a variable. So you don't have to do a product rule here. We would just use a chain rule. So this would just be like S squared e to the st. And so now if I plug in infinity, like -1 all over S squared e to the s times infinity, well, this just be turned into like -1 over infinity, and that just equals 0. And once again, that's the case if s is greater than 0. So, coming back down here, okay, we know this turns into just 0. So maybe I could say like 0 right here with a different color. And we know this term goes to 0, so we could write -0 minus, we know this term goes to 0 by plugging in infinity, and then if we set that s is positive, so this is also 0, minus 1 over s squared times 1, which is just 1 over s squared. And this is if s is greater than 0. And so we clean this up, distribute in the negative. What we get is a Laplace transform of 1 over s squared if s is positive. So therefore, the Laplace transform f of s is 1 over s squared for s being greater than 0, meaning positive. So that's our Laplace transform for a basic function like t. Okay, so linear functions like t, this is what they generally end up with, just depends on the coefficients. But this is the general form and the way we get that. All right, so we can add this to our toolbox as well. But that's it for this video, okay? Sometimes the Laplace transforms take some work and your previous calculus knowledge, like integration by parts, and then using L'Hopital to solve a infinity over infinity situation. All right, so bringing back some of that calculus fundamentals. Well, that's it for this video. Thank you for watching. We'll be trying out some more examples. All right, take care.